He did a PhD in Paris and now is in Amsterdam. And he does this very funny work with metamaterials. So Corentin, please, let's start with your first lecture.
Okay. Yes, thank you very much, Carolina. Thank you, the organizers, for having me here. Can you hear me well with the speakers? No? It's... Ah, okay.
Okay, now it's working.
So, is it better? Yeah, I think it follows me, no? Ah, yes. All right. Yes, as you can see, I'm going to talk about not disordered stuff, but that's maybe doesn't fit as much my personality as disorder would, so that's why I'm very happy to be in this school. But yes, indeed, the topic of the day is, I guess, the ordered counterpart of, let's say, a disordered elastic network that you've seen a lot about during the last week and this week. And these are, as opposed to what we heard, for instance, this morning with Fred, also with Andrea, these are carefully engineered, architected. It is not evolution that makes them. It's a 3D printer. And because you can organize the building blocks as you want, you can make it do stuff. And so as a result, these objects, and we have here one example, can, for instance, change shape as you want. And so the bulk of the questions that you have seen last week and earlier this week were how to understand, how to bridge the gap between micro and macro, how to understand emergent behavior. And there's a lot of that here as well. But what we do is mostly we ask the reverse question. Like, I want a smiley face. How should I program my 3D printer to arrange the building block to get the smiley face, right? And so in a way, this is really a kind of a modern example of what a composite is. So composite materials maybe exist since the 50s. And typically, you have a material that is a mixture of material A and B. So A is steel, B is concrete. What you get as a result is A plus B, reinforced concrete. And what you get is a mixture of the properties of A and B, right? And so composites are very successful in our daily life. But that's about, and also very interesting from a fundamental point of view. But that's about this, right? So you have A and B, and you get the properties of a mixture of A plus B. What metamaterials claim to do or aim to do is to actually, you mix A and B, and you get a material that has completely different properties than A and B. All right? So you mix rubber and air. No rubber and no air makes a smiley face, but the mixture does, right? So that's the idea, and that's actually the very definition of metamaterials. These are materials that are that have properties that escape that of their constituents, right? And so another way to think about, well, and actually this is not entirely meta beyond what's in nature, because if you actually look at some natural materials, they also have some properties that you can't find commonly. But that's because of their architecture. So if you read that book, actually, this is the guy who discovered elasticity. And he has an old book with all observations of nature. It's actually a beautiful book. And what he did is he put a slice of cork under his microscope, and he saw that there was kind of a honeycomb-like architecture. And in fact, cork is an interesting material. We heard about Poisson ratio this morning. The Poisson ratio tells you whether the material expands or contracts when you compress it. And this material is actually useful for bottles because it has a 0 Poisson ratio. It doesn't expand when you compress it. That's why you can get it out of the bottles. And this property largely stems from this architecture that you have. That's really, that's really one of the observations, let's say, of Hooke. Okay. And so if I zoom in, this is basically the game. Usually when we think of materials, we think about composition, we think about how atoms and molecules are arranged, and we think then at the scale of the nanometer or micrometer. On the other side of the spectrum, you have engineers, and they're used to thinking about large structures. They can arrange beams in the way they want. And they can make also interesting machines, interesting structures out of that. The idea here is to really blur the boundary between these two worlds. So use the tools of material science, condensed matter, and together with the tools of structural engineering, essentially, to create objects that have interesting, peculiar, counterintuitive properties that might be useful for applications. Okay? And so, as I said, I think what's interesting is to explore this idea of relationship between structure and property. So if you have a structure, can you figure out what it does? This is the easy part of the question. But then what's much harder is actually to go back and say, okay, given a target function, what should I do? What should I print? What should I fold? And actually, yeah, I'm going to be a bit of a spoiler. It's, despite maybe 10 years of effort, I've been in this field for now about 10 years, we're still hopeless in answering that question. It's still, I'll serve a few examples, and somehow we're very far from having a very systematic tool to actually go from the target to the structure. And so what I'll show you is how, what some of the effort that we in my group and some others have done, but you also, I also will show you how desperate we still are to find proper tools to do that. And then there's also an interesting question: is how far can you go? How crazy of a response can you do? Can you make a material that has, properties that are very different from A plus B, but also some materials that have, responses that don't have responses that are not that of materials, but more that of machines. And that's why I like to call my lab the machine materials lab, because those materials actually also blur the boundary between objects or materials and machines. Okay, and so. I like to think about metamaterials or mechanical metamaterials and divide them into 3 classes. And so this is the stuff that engineers like. You make very lightweight and strong materials. And this is, one of the examples. Some other people like to make waveguides. So you can, guide sound very robustly in a channel. And some other people, like me, like to make shape changers, objects that change shape. And reconfigure and can also absorb a lot of energy. Okay? And so in the talk, I believe that what Xiaoming is going to talk about today and tomorrow is, I think, between those 2 words, perhaps, but a lot more waveguiding than I will. I will talk on waveguiding objects on the last day on active metamaterials, but I'll focus mostly on shape-changing objects. Okay? So before I go on and give you a full outline. Let me tell you about. Oh, this is the boring slide where stuff is being 3D printed. Hopla. Yes. Okay. Let me tell you a bit about applications. So what can we do with these metamaterials? So I think they can raise interesting fundamental questions about inverse design, about trying to link geometry to properties, especially making analogy with condensed matter. But I think it's also it's also an exciting field because applications are not too far away. And I think it's interesting to keep in mind, also as a source of inspiration. And so I'll survey a bit of some of the applications. This is an obvious one. If you have a lightweight material, well, you can put it on planes, make in cars, aircraft, spacecraft, and so on. So potentially you can make going to space or traveling cheaper and safer. Okay, I'll show you an example of that. As I said, you can make waveguides. So this one was one of the first examples where I actually showed you could robustly guide a wave. So this wave is going around without backscattering, so it's very nice. And so this was, obviously maybe perhaps not a very useful wave, although you could think of maybe harnessing some low frequency waves for harvesting energy from the sea or from vibrations. But those wave guiding devices now can, for instance, the same principles can be made much smaller and much faster here at the megahertz, and you could imagine that those objects could, for instance, go in your phone. Right? So this is potentially interesting. But again, I won't talk about that. I think maybe one of the most interesting aspects of instability is that you can use them for dramatic shape changes. So this is an example of a kirigami. So it's a sheet of paper that is cut. And what people have done is just put solar panels on it. And you see that if you stretch it, the panels deform. And potentially you can have adaptable solar panels with less actuators, less motors. And so that's potentially an interesting option. You could also think of metamaterials in a spacecraft, for instance, for unfolding solar panels, as I said, and for robotics, which is actually one of the fields which is developing one of the fastest developing fields at the moment. You have something very flat, and you can unfold it, and it can walk away. And so you use the instability, the folding, not only to shape change to get into the shape that you want, but also to locomote later on. Okay. I think Itai is doing very interesting work at the very small scales along this line, which is really uses the fact that it's very easy to make things in 2D. And so the question is then how you make a machine that moves in the 3D world, even though you can only fabricate it in 2D. I think that's potentially a very interesting, compelling avenue. People have explored that not to explore biological world, but to work on the Harvard campus. And so that's a similar principle. You have a kirigami object. It changes shape. Because it changes shape, it has an anisotropic friction. And if you couple it in a smart way to an actuator, you can make an object that can crawl only using that object. So it could be useful. Okay. Last example, when we go more towards potentially what's useful with respect to us. So I talk about engineering applications for aerospace, waveguiding, robots. But this object is actually, I think, a model of a stent, so that could go in the body and prevent aneurysms by just you send it there, folded, it deploys where it needs to deploy, and then protects you from an aneurysm, for instance. And so that's also, I think, a field that's quite interesting for metamaterial field, an area of application for all this relationship between materials and humans, or better use materials to improve healthcare, for instance. And so these are other examples where you can use metamaterials that falls to potentially use as prosthetics. All right, and you could also think of the same for prosthetic orthopedic shoes and so on. Okay. Last example before I move on is actually one thing we explored recently is how you could use metamaterials to also maybe improve relationship between materials and humans. And what we actually did was to see whether we can actually use metamaterials to improve mouthfeel. So when you bite, you actually do a mechanical experiment. You put something in your mouth, you compress it, it breaks. And so if you can control how an object deforms and breaks, you can potentially control how you feel when you bite it. And so that's what we actually did a very early step on by printing some of this chocolate structure with given shapes. We broke it in the lab, recording the sound. You see it breaks in some interesting way. And then you can correlate. You can see whether when an object has more cracks, people feel more cracks. And that actually was the case. And so that's an early exploration of what you could do to potentially use metamaterials. So usually I'm more excited about engineering, waveguides, robots, and so on. But somehow this study really spiraled out of control. So the news, the media really found it cool. So you have all the I don't know. I think the community outreach office of my university estimated that like 25 million people having read that article. I was very proud that I was interviewed by the Swiss radio, which is the land of the chocolate. And actually last week there was even 6 months after there was a piece on the Washington Post about it, so that was fun. And I even found something from Brazil, so I think this is the Portuguese Brazil outlet. So that's also a lot of fun, but I think there's actually potentially some value and some interest in thinking about fracture. For me, it's also an interesting way to think about, I guess, a source of inspiration, let's say, for how you could use metamaterials. And then again, if you ask me, okay, but how can you can you make me feel, can you make a piece of chocolate taste like pizza? I think we're very far away from being able to design a mouthfeel, but that's actually quite a stimulating question you can ask. Yeah. And so this was like a broad introduction to metamaterials, why I think it's potentially impactful and interesting. And before we go on to the details of the science, really, I'm happy to take any more of these general questions or questions along those general lines, if you have.
Can you do the perfect, let's say, carrot or, I don't know, vegetables? You know, it's like it would be useful for kids, isn't it?
Yeah. No, in fact, we initially started, the student who did that ended up preferring chocolate, but we initially started with some mix of Unilever that's extracted from a biofiber blend that is, a gluten-free, fat-free, biologically sourced and so on. And so I think ultimately, yes, you can get there, right? There actually, after this piece in the Smithsonian here, a woman from the US wrote to me, oh, I have an eating disorder. Whenever I eat something, it takes me 5 hours to digest. Can you help me?
Really?
So I think having objects that are easier to digest for people with this kind of eating disorder could maybe help. Yeah.
Okay, the near future then.
Yeah.
Is there any other question? Okay.
All right. And so let's go to the course, to the structure of the course. So this is what I designed. Today is going to be, we have 4 lectures, so we're going to do something quite light in terms of content. But it's just to give you a feel, like how do we intuitively think about metamaterials? How do we intuitively think about geometry, and so on. And that's going to rely a lot on the tools that Tom Lubensky introduced, but also the one that Xiaoming introduced. And so I think it nicely overlaps. And then I'm going to show you that you can also go towards the design. So I'm going to tell you basically what's underlying this smiley face. And also I'm going to discuss alternative approaches, what other people have done. And that's going to be tomorrow. And then we're going to go beyond. So we will design stuff, and then we'll figure out that what we have designed we actually don't understand. And then I will show you that actually some interesting things that emerge that we haven't programmed in, that there is. And then I'm going to talk about objects that move by themselves, that are active. So not necessarily about geometry, but how to actually control how energy is injected in those materials. Okay. And so today on the menu, no chocolate. Sorry, Carolina, but how do we think about metamaterials? How do we think about intuitively, and how can we go beyond intuition? Okay, and so this is the idea. So we talked about Poisson ratio. So this is my very basic sketch of a negative Poisson ratio. You have a block of material, square. You compress it from the top, and a material that has a negative Poisson ratio. What it likes to do, it doesn't like to change its shape, but it likes to change its volume, right? So in other words, if you compress it, it will try not to deform into a rectangle, but remain a square. But then since you compress it, it will just make a smaller square, okay? And so that's what is depicted by the blue arrows there, right? So that's, I think, the prehistory of metamaterials really is rooted in that example, so that's what I talk about it. And then the question is, okay, all right. This clicker, yes. The question is, okay, now I told you that we make a composite. So we actually are allowed to do stuff to a material, to punch holes, for instance. Or I can make a crease, or I can make cuts, or I can even make a knit out of that material. And the basic question is, okay, how do I do this? I want this. How the hell am I going to put my holes or my folds to do this, right? And yeah, I'll show. And the idea now is I'll show you a bit of an intuition about it, and I'll show you that the only thing we can do so far is start from examples that some smart people figured out, and basically do variations around it. But doing that from the bottom up, from scratch, I don't know many examples. Actually, I don't think I know actually any example of a systematic approach to do that from scratch. But no matter what, it's still interesting to think about how, start from well-known example and try to understand how the well-known examples actually work. So imagine, so this actually were two people who actually also were amongst the pioneers of this field, Milton and Cherkes. And they have a very nice paper which is called which elasticity tensors are realizable. So the question they ask is, okay, imagine someone gives you two material, a very stiff material, which is here the white, and a very soft material, which is here the one with the dashed or the dotted. And so, and you can arrange it however you want. Can you make any elastic tensor? Right? And the answer to the question is yes. And so the idea is to reason as follows. So imagine here I have these rigid bars in this soft, very soft matrix here. How many elastic? In how many ways can I deform that object easily? Yeah, I think you got a. And shear. Yes, yes. So you said two. And is there like a stiff, something you cannot do? Yeah, you can. So this object, in 2D, you need actually 3 elastic moduli to characterize the response. And so there's, you need to think about 3 things, right? And actually this material, as you said, had 2 soft, 2 squishy directions, and as you said, one's stiff. So I can do this, but I cannot do this, right? Right? And that's because of the way the material is arranged, right? Now let's add some things. Let's see, okay, now if I add some bars, how many soft directions and how many stiff directions do I have?
Sorry, can you say what's solid and what's air?
The white is very solid, and this one is very, very soft. Yeah.
Yeah, okay.
So very stiff, very soft. So you said too soft? Okay, who agrees?
Only one direction.
Too soft, only one direction. Who agrees with?
Too soft, one direction. What do you mean too soft, one direction?
Yeah.
You can only shear by this way, but but it links the two directions.
It's a combination of, like, you have a projection of compression and shear.
You're going to give the microphone to... yeah. That's my evil plan, to have actually the audience explain.
Okay. Is it on? Okay. So also like what Itai just said, so it actually has a combination of a shear and compression. If you shear it in a way that also reduces the distance top to bottom so that the stiff rods rotate, then it would be compliant to this.
So how many soft directions do you get at the end?
1.
1 and 2 soft stiff. Who agrees with Ben? Who disagrees? Oh, there's a lot of people who disagree.
Maybe disagree, everybody disagrees.
So who disagrees and why? Is there someone who disagrees?
They're cheating. You have to vote. We're not being graded on this. Okay, ask the question again.
Yeah, so how many? So Ben said there's 2 stiff direction and 1 soft. And so who agrees with Ben?
Sorry, he said there's one soft.
1 soft and 2 stiff. Yeah.
It's also seen that you work the symmetry of shear, isn't it? That you can only shear in one sense.
That's what you said, right?
Okay.
Yeah. 2 soft and 1 stiff. So we have a disagreement. Good. So why do you, Ben, do you disagree? Why do you disagree with Lawrence? What's your name?
So I think that it is linked that when you shear, you're going to also have. So I think that the shear here is joined with the compression in the vertical direction to be soft.
I have a question. Are those points hinged?
Yes, they are hinged.
Yeah, but I mean, probably the shear tensor is anisotropic.
Yes.
I mean, there is
Yeah.
one privilege
Yeah.
direction. So that is one stuff, and the other one is the previous one.
Yes.
But you can share by the opposite way.
Okay. So so I disagree with you because if I shear, so this is my arms are the bars. I can do this. I can shear back and forth, right? So I can actually shear to the left or to the right, right? What you have in mind is that if you do that a lot, you can only do it in one. You can do it much easier in one direction than linear. But now I'm talking about the elastic moduli. I'm talking about the linear response. So I'm talking about what happens when I do it a little bit. And as what Ben said, if you do it a little bit, when you shear, actually, you also dilate. So you have this dilation effect that comes. But what you can do to actually make your life easier is, diagonalize the system. So diagonalizing here means like you just rotate your head, and then you can do the same exercise with having your head rotated with the same angle as the bars. So then I can see that I can push. I cannot really push against the bars, but I can shear transverse to the bars. Right? Okay? Okay. So let's continue. Let's add more constraints. So now what happens? Do I have any soft directions left? I had one left.
Where this can collapse in. But that will depend on whether, yeah, I think it depends on the compressibility, but we can probably collapse it inwards.
If you compress here, you're going to squeeze the white bar, no? And you're not allowed to squeeze the white bar because they're very stiff, right?
But if there's like a gap between them, then they can.
Yeah. So I guess maybe my drawing is a bit bad, but this is hinged. This does not allow to slide.
Oh, okay. Then
Right?
no.
So if I sharpen my question, what do you say? Like that? If the bars are just allowed to rotate about their hinging point, not sliding? Do you still keep that soft direction or not?
No.
No. Okay. So indeed, what you have is a very stiff composite, and you lost all the soft directions you had. Okay. So then you might want to ask me, but why the hell bother? Why not use the white material only, right? Well, the answer is this. It's actually what allows you to do. If the typically weaker materials are much more lightweight, so if you do this in a smart way, you can actually make very lightweight materials. And actually, this object, I think, this is a lattice that has the density of air, but the elasticity of a very soft rubber. I think. And so potentially that means that you can have a very lightweight yet object that has some mechanical integrity. Okay. Not only that, but you can also control this by controlling the geometry. So it's also, I think, an interesting side of metamaterials is that you actually have this tunability that you get. Okay. Okay. So let me just illustrate you another example of how. Yeah.
What's the Young's modulus of the material you're making it out of?
I think it's metal. Metal.
That's probably gigapascal.
Yeah. Metal is 60, 90 gigapascal, I think. Yeah.
So that's basically Young's modulus and volume fraction to the second power.
Yeah.
Metal foam does that.
Yeah. What? No.
I think you just make a metal foam, you get that.
No. No.
She has, Miss Julie has,
Yeah, Julia Greer.
right,
Yeah.
so she has essentially tubes that she makes. Not
Right,
just-
no, but I'm saying if you take a metal foam at that density, you don't get about that much. Okay, so that might be an improvement.
No, the thing is, you cannot beat the thermodynamic limit with this, but you can get very close to it, I guess, right? So, there's thermodynamics tell you how lightweight tell you or gives you a constraint between the Young's modulus and the density of your material, and there's an upper limit. There's a ceiling you cannot go above, and yeah. But I agree with your scaling argument. That's actually the way. But not any metal foam, because any metal foam, a standard metal foam. Well, let me just give you. Let me give you an argument still. Any metal foam would have a disordered structure. Here, if you have a carefully arranged structure where all the beams contribute to the strength, that will be much stronger than if some of the beams are already pre-bent and start to bend. You know, so. Exactly, and the ultimate strength that you get is when the structure starts to collapse, is much stronger if your beams are, tend to have to be loaded in compressive directions rather than bending direction. And so typically what allows you to approach this thermodynamic limit is really to have a special architecture where those beams are really, kind of not bending when you start to load them, but they really have to be loaded actually. Yeah, so that's kind of the intuition I can give there. Yeah. Okay, maybe let me come back to the Poisson ratio, give you an intuitive example of how geometry not only can allow you to control how many soft modes you have, but also their shape. Okay, and so this is the same. The lattice is very similar. It has the same topology, but here the only difference is that I've slightly distorted the lattice into this one. Okay, and one of them has a positive Poisson ratio, and the other has a negative Poisson ratio. And so we're going to make, again, a little quiz. Who thinks this one has a positive Poisson ratio? I remind you, the positive Poisson ratio is you compress, it expands. About, yeah, we have more than half, so yes, this is correct. And so the way you can understand this is if you just take a unit cell, for instance, like this, you have multiple ways of choosing a unit cell, but here I choose one. And so you see that this is denoted by these bars here. And so when I compress these bars like this, they're going to be squeezed. And so the overall unit cell is going to be larger.
So here again, your notation is that white is something stiff.
Yeah, white is very stiff. And then that's not my notation. Actually, I took those from that paper. But yeah,
okay, not just because I'm having bad time in understanding that. So okay.
Yeah. Yeah, punching holes. No, here they had actually they are very they're from Utah, I think, very religious state. And so they start that paper like, imagine God gives you two materials, one soft, one stiff. Could you do? So it's actually a fun read. And so yes, so these bars are very rigid and they can freely hinge about each other. And the matrix here with dots is just very soft goo, basically. That gives it some elasticity, right? And so the idea is that you can think of it just as geometry because you can just imagine. So I guess what I want to give you is an intuition of, imagine how this object would deform, right? Clicker is dying, so I'm just gonna. And so this is what happens, for instance, for the unit cell on the left, but for the unit cell on the right, it's the opposite. So it's me, and if my structure is reentrant like this, when I'm being squeezed from the side, my unit cell becomes smaller. So this is a negative Poisson ratio. Okay. Good. And so actually, this was the first paper. One of the first paper, or the prehistory of metamaterials, was born in '87. And so this is a way. This is to illustrate that indeed through geometry you can understand the positive Poisson ratio by just focusing on how those bars hinge about each other, right? And actually how Rod Lakes in '87 devised this foam. So he had actually very smart way to devise a foam that you see when it's stretched becomes fatter on the side. Okay. And here the intuition we had on the slide is actually very similar. You have these internal rotations that actually give the effect that you want. Okay? So that's it, really. I mean, so basically what I want to tell you about today and tomorrow and Thursday is really how to think about those materials that have rotations. So hardly any stretch in the bonds, but mostly rotations between the bonds. All right. So I think it's a bit of maybe the flip side of what Fred said this morning, where he was focused mostly on, I mean, in this morning there was like two regimes. Regime where things rotate and then starts to stretch ultimately. Here we focus mostly on building blocks that just purely rotate. And so if they purely rotate, they do not elongate any of the springs. And so then you can just actually think about them by looking for motions that do not deform any of the springs, and that's what Tom and Xiaoming actually discussed last week and yesterday. And so that's what we're going to do. We're going to see beyond intuition that I start to develop here, how geometry control mechanics, and whether we can go beyond intuition. Okay? And the idea is to use, again, this Maxwell-Caladine counting argument. We're going to start with that. And so this is actually I guess maybe that's what connects this lecture to the rest of the school. Is that the Maxwell or the physics of disordered materials actually is very connected to the physics of metamaterials because it comes from Maxwell-Caladine, so it comes really from that formula that I guess you have discussed. And so if I have an object here, a frame with degrees of freedom, so nodes that can move in the plane, that are constrained by springs. You see that I guess you've been acquainted with two types of objects, two types of object in this object is that floppy motion. So if you, for instance, slide over these nodes on the top, they do not then deform any of the bonds, right? And so this is called the floppy motion, a floppy mode. On the other hand, in the bottom, you see that here you may have tension in the bonds. So the bonds might actually have some strain or some stress in them, but then the net force on each of the bonds, on each of the nodes, add up to 0, right? And this is called the states of self-stress, okay? And anytime you want to design a flexible metamaterial, well, the first way to actually analyze or understand what's going on is actually try to figure out whether it has floppy modes, whether it has states of self-stress, and how many of them it has. Okay? All right. And so now we're going to, I think you've seen that, right? I guess you've showed them that formula, Xiaoming, right? Or,
I did not, but Tom did. I think.
Okay. Okay, Tom did. So I don't want to introduce that formula again. What we'll do is just play around and toy with some examples so that you can get used to how to use it. Basically, if I recall what the formula says, is that this structure has some solid body motion. So here in 2D, it's 3, because this object, if it's not pinned to the ground, can just move up and down and can rotate. So that's 3 solid body motion that don't deform any of the springs, right? And so here you can generalize it to 3, right? So that's why people like sometimes to write this formula, because this formula here is equal to 3 in 2D and 6 in 3D. So that's a convenient way to pack it all up. So 3 plus the number of floppy motion minus the number of states of self-stress is equal to the number of degrees of freedom minus the number of constraints. Okay. So if I just write here as a recap, in that case, so we have 3 here. Here we have 1 floppy mode, the one I drew, so 1 here. So and 0 is 1 here. In our case, right? Then we have the number of states of self-stress. I drew 1, so there is 1, right? And number of degrees of freedom here is d. So d is 2 in our case because we are in 2 dimensions times n, and n is here. I have 6, right? 6. So this is 12. And then NB is the number of bars you have of constraints that constrain you. So here you can count how many bars. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Okay? And so here we have 3 plus 1 minus 1 equals 12 minus 9. Okay? So I think we're good. Right? Okay. So that was the recap. So I did my work. Now it's your time to do some work, where we're just going to cover a few examples. And so let's see. So actually, for this, I'm going to ask you to pull out your cell phone or your laptop or your tablet. And you're going to have to go to this wooclap.com. And once you're on wooclap.com, you fill in that code. So it's not very, I'm just going to write it also here, that it's easier. And then you enter the code JCG. GHIC. Okay. Okay. JCG.
Does it need to be capital letters?
Yeah, capital letters, yeah. JCGHIC. Okay. And so here, it's a multiple choice question, so I filled in 4 possible answers. So 0. So what the question is, what is the difference between N0 and NS? And you can answer 0, 1, 2, 3. And the system I'm asking you to actually study is this origami vertex. It's not working.
Oh,
Does it work?
the JC.
Okay. Let me check. I should start it, maybe? No. No? Okay. Yeah?
Last I should be a J.
Oh, okay. Sorry about that. Does that work to do that? So this is a origami vertex. So if you want, I can help you think about it. So each plate, you can actually decompose it as a triangle. All right? So this is how you can think of this as a bunch of masses and springs in 3D. You have here those masses that are related by constraints. And so here what I'm asking you is to apply the formula up to tell me what's the difference between N0 and NS for this vertex, origami vertex that has 4 folds. And I can see, yes?
Are we considering 3D or 2D?
Yes, 3D. It's living in 3D, right?
Could you go back 1 slide to see the definition of each?
Maybe it's better if I keep it there because I don't want to lose my, so this is, all right. So D is the dimension of a space. This is a 3D, these objects live in 3D, so D is 3, right? All right, so this is what you have to guess. All right? And this is, it's showing the results, it's showing the votes.
Yeah.
Yes.
And you want this considered as a 3D object?
Yeah. It's a piece of paper really that is living in a 3D space. Okay. Okay. So if I repeat, this is the number of solid body motion you have. So 3 in 2D, 6 in 3D. Then this is the number we want at the end. And this is the dimension of the space and the number of nodes. And this is the number of constraints that you have. So how many bars constrain those nodes?
Sorry, I'm lost. Are you asking about the example that is in the blackboard or the example that is on the...
The example on the board is the same. It's my abstraction of what's here.
Yeah, but how do you read the example that is in the... What that means? I mean...
I can play it maybe.
Yes.
I can play the video. So this is the stuff that we're talking about.
Ah, okay.
Yeah? Something that you fold, okay?
Okay.
Yeah? I don't want to play it too much, it spoils it, but yes. All right. Good. We have already 16 votes. So I'm going to move on, if it's okay. But indeed, the correct answer here was, actually I can use my thing. Oh, the correct answer was 1. So there's 1. If you do your counting correct, what you find is n naught minus ns is 1. That doesn't tell you how much n naught is and ns is. But here, the people who played with origami know that if you have a full fold, you can actually fold it cheaply, right? Okay. So there's no tensor self-stress as a single floppy mode in here. Let's do it again now with 5 folds, right? I'm new to this, so click on the screen. Okay, so same game now with 5 folds. All right. Okay. All right. Yeah?
Okay, the following question. So actually the constraints that we have here are planes, right?
Yeah.
And in the case of triangles, this is the same as putting on a...
What do you say? You said the constraints we have here are planes. What do you mean?
I'm sorry. So I mean, if I imagine it as an object like this, like your abstract representation.
Yeah.
So just fixing the length between these 3 nodes is equivalent to fixing the plane of paper without deforming it not along a track. But if it were a square, then you would have to draw the constraints differently in order to guarantee that satisfying the length would satisfy the entire plane, right?
Yeah. So what Ben is saying is that here I somehow told you to do the counting by abstracting this piece of paper by nodes connected by bonds, right? but this is not the only way to do it. You can also do the counting by saying that you have plates that are constrained. And so if you have a plate, each node in 3D is 3 degrees of freedom, but each plate now is 6. And now when I connect 2 plates, I actually constrain 5 degrees of freedom to keep one. So you can also do the counting by not considering the nodes, but you can also do it with the plates, indeed. And then it's different every time. And so there's not one way of counting. You can do it as you like, as you prefer, right? Does it answer your?
Yeah, but I mean, okay, I guess you can always do plates, but if you want to look at I think the nodes and distances are simpler.
Uh-huh.
And I'm just saying, if you have a plate of a different shape.
Mm-hmm. Like a quad instead of a triangle, you mean?
Yeah.
Or?
So is the rule of how many?
No, because if you don't have triangular plates but square plates, if you assume it's indeformable, then you can also just use that for counting. I don't see why not. Yeah. Yeah. But then if you imagine I have an origami that is made of I don't know, I have 2 vertices, something like this, or like more vertices, right? Whatever. So here I have a quad in the middle, right? If I keep my counting with balls and springs, indeed I have to add an extra bar to triangulate it, right? Otherwise this plate will not be undeformable, right? So you have to, it's really, I think that's also what's fun about this exercise. Maybe it's like you have to think about how you abstract this into this, right? So, and there's not one single way of doing it, right?
But even this extra, you need another bar.
Yeah, you actually need 2 bars, yes, indeed, yeah.
I was asking if there is a generalization, so you know, okay, triangle is enough, for 4 you need to add a cross,
Yeah.
and if you look at some other, you can add angles.
No.
Stuff. If you want to stay with just bones and linkages, then you need to add an angle instead of rectangle circles. So that's the way you replace it. So generally, you say that if you have a face, you can replace the face by angle constraints of the bones. And you don't need to add the linkages to it. That's the way.
I don't think there's a single one. Imagine you have a square, a rigid square, and you have 2 rigid squares, right? So you can do that by assuming the square is a solid body object. So in 2D, it has 2 modes. But you can also, add whatever, how many nodes, however many nodes you want, right? It just makes your counting a bit redundant, right? So I guess because then you have a lot of steps, you will have you have a lot of constraints that compensate for the extra node you put, right? So I don't have a systematic way besides just being as lazy as possible, which is have the smallest number to count, I guess. That's my. Actually, the next example is quite good also for that. So this is the chain I think Tom introduced, and I think Xiaoming will also discuss. And so here there's not more than one way of doing the counting. And here, so we have the same quiz again, and here I encourage you to be lazy. So just so you know, these are anchored in the ground. These beads are freely rotating around this anchor, right? So you have like these red are basically rotors, right? And the rotors, so this guy can just rotate like this, and the next rotates like that. But these rotors are connected by a bond, a spring. And so here there's more than one way to do counting, and I think the best way is the laziest way probably, but yeah. So let's see, I can try to activate this. And so here the question I ask is, but that's,
But they are fixed in space, right?
they're fixed in space, yeah. Yeah, no, this is fixed to the ground here, right? The springs are blue, yeah. Yeah. So if you wish, I can make a more serious drawing by drawing something like this. So I attach it to the ground. And then there's a link here, right? So this is attached to the ground. This bead is attached, is leashed to the ground by this bond. And that's it. Yes.
English wise are not springs, right? It's just one
In a way, the red bonds and the blue bonds have the same status. They are just a bond that constrains what you have. Right? Yes, and so here I ask you more than just telling me I can only activate one at a time. Yes. So here I hope you have seen that with Tom. So I ask you more than just n naught minus ns, but I ask you n naught and ns separately. So on the left, I ask you how many floppy modes this thing has, and on the right, I will ask you how many states of self-stress this chain has. Okay? Mm-hmm.
Show the answer for the last one.
For the last one, it was 2.
Okay.
2, yes. Yeah, the majority was right, yes. I can publish the results afterwards, but yeah, it was 2, yeah. Say it again? This is now in 2 dimensions, yes. Yes. Life is hard enough. No, this is an open chain, so 9 rotors, 8 springs.
Wait, but the rotors can rotate?
The rotors can just do...
No, but it is in plane or?
In plane, in plane.
In plane, one that will.
Yeah. So this guy can just do this, right? Yeah. This guy is fixed in the ground, yes. Do we have colors? The red rotor is anchored in the ground, so it can freely rotate like this. So if you wish, each rotor has 1 degree of freedom. Yeah. Yeah. All right. So I'll move on, and the majority is right. So very good. It's 1, and naught is 1, and actually you can see it because it's on the right. And the reason why you can see it on the right is, imagine you distort a bit your geometry such that the last blue bond is parallel to the rotor. You see that if I start to rotate the bond, but then I'm attached my rotor, my spring, my bond, blue bond is attached there. If I'm purely parallel to my spring, you see that to linear order, I'm not going to deform the spring at all when I'm collinear with the rotor, right? So that's why intuitively you can see that you have a floppy mode here, right? In the case where it's not exactly collinear, like I drew, it's still a floppy mode, but it changes a bit its shape. Yeah. Okay. So now, if you know the answer, if you know the answer that there's 1 floppy mode, and if you do your counting right, you should be able to deduct how many states of self-stress you have, which is the question here. So in how many ways, is there any way in which you can have tensions in the bonds that do not add any net force on each of the nodes? This is the question. All right, we have to move on because there's other stuff I want to discuss. But indeed, the majority is correct. You have 0 states of self-stress. And that's because if you do your counting, you have 9 rotors, so 9 degrees of freedom, because each rotor is 1 degree of freedom, 8 bonds, so 9 minus 1 is 1. 9 minus 8 is 1. And since every rotor was spinned, you can actually completely discard the number of solid body rotation because it was discarded from the initial count we did. Okay? Yeah. Yeah.
Having only one floppy node,
Mm-hmm.
how do you, like, okay, you gave us the argument about the rotor on the right, but
Yeah.
why is it different for the rotor on the left?
Because here, imagine if I have my arm on the left like this, and my spring, my blue spring is completely perpendicular to it. That's kind of the counterpart of being collinear. That means that, you know, to linear order, when I start to rotate my rotor, I will move this. No, it can. Yes, in fact, it can. That's my next slide. Thanks for the transition. So now we have this chain. This chain looks very much the same, but it's not exactly the same. And I'm going to ask you the two same questions. So how many floppy modes do we have in that chain? Yeah, what is the difference? That's the question. So here I draw the same version, but slightly in the case where actually these bonds are collinear, so that you can see. Do you see the difference with the previous chain? Look at the edges. So this is topological. You have to look at the edges. This is also the kind of the, let's say, asymptotic limit of this one, where I drew exactly the springs collinear to the rotors. Before we had one spring and one rotor being collinear. Now we don't have one anymore. Right? It's fun to see people. All right, we have 2-hour response. The majority is voting for 2. And indeed, it is 2, because if you look at the edges, you see that I have 2 rotors that have a collinear spring. So that means that if I start to rotate that rotor, it's not going to change the length of that spring to linear order. right? It's going to change it to quadratic order, but not to linear order. So that means that we have a floppy mode here and here. So we have two floppy modes. All right? And so now, if you do your counting right, you should know how many states of self-stress we have. The counting didn't change because the topology of the lattice was kept the same. So how many states of self-stress do we have now? Actually, I gave the answer. Yeah, so we have one here, indeed. And as you see, the states of self-stress is really depicted by these arrows. So imagine you have this central node here can host a vertical force towards the top. And here it can also host forces in the two bonds that are on the side, such that the net force is 0. And that is actually the states of self-stress that you have. Right? So you see here, this counting that we have doesn't really tell us more than, it doesn't tell us more than the difference n naught minus ns. But it's still nonetheless useful because if you figure out the number of floppy modes one way or another, you can actually know the self-stress and vice versa. Okay? Cool. All right. So that's it for, and I think you will see more of this chain maybe with Xiaoming, I believe, or at least related lattices, where not only you can use your intuition, micromechanics intuition to tell where the states of the zero mode and the states of self-stress are, but you can also borrow tools from condensed matter theory to predict when the edge modes, the floppy modes of the states of self-stress will move. Okay? Since we're in a disordered school, I still have a disordered slide, and that's my most messy slide. So this is a picture I randomly took from a disordered paper, maybe one of Andrea, in fact. And just to tell you that you can actually do the counting argument also there. And we had a lot of this counting with Fred this morning. So imagine you have a lattice, right? So if every lattice has nodes and constraints, and when you're disordered, you can look at ensemble averages, or you can look at spatial averages. And so typically, imagine you have a network that has n nodes. So dn here is equal to 2n, where this is the number of nodes. And the number of constraints in a disordered lattice, you say that every node has on average z neighbors. So you can say that the number of constraints is actually z divided by 2, because each bond is shared by 2 nodes, times n. Right? So when you do your counting, what you can say is that you have then d plus 1 over 2 plus n naught minus ns is actually equal to 2n z 1 minus z divided by 4. Okay? Okay? And so, which means that if you look on average, we saw this morning in the lecture of Fred that ZC was equal to 2 the dimensions of space, so that's a critical isostatic number. So in 2D, that is 4. And so what we learned from that is that if Z is smaller than 4, then we have n naught minus ns plus, I still keep on writing this one, is going to be proportional to n, because this number here is going to be bigger than n, which means that when you're under-coordinated, when z is smaller than 4, your number of floppy mode grows with the system size. Okay? If now z is larger than 4, so if you're hyper-coordinated, what you mean. So typically, this what you can imply from this, sorry, is that n0 is growing like n, and that ns is typically of order 1. Okay. On the other side, in this case, what you have is that well, this one was actually an exact result. I don't need to approximate it. So this one was 2n 1 minus z over 4, and this was a positive number. On the other side here, in the other limit, 1 minus z over 4 is a negative number, which means that typically what you find is that the number of floppy modes is of order 1 or 0, and the number of states of self-stress is growing with the system size. Okay? If you're around 4, on the other hand, what you find is that typically the number of floppy modes is typically of order 1, and that the number of states of self-stress is also of order 1. Which means that when your average coordination number is less than 4, or less than 2D, you have a very floppy network that is full of number of floppy modes. When, on the other hand, you have a hyper-coordinated lattice, you have an average coordination number that is more than 4, then you have your network full of self-stress that has hardly any floppy modes. And exactly at z is 4, or around 4, then you can have anything, right? If you can have anything that will depend on whether you had pre-stress at the boundary, like Fred discussed, or if you have some specific symmetries in your lattice, which you typically don't have in a disordered lattice. Okay, so that's kind of the, basically the. Well, this is the way to just revise what we just heard this morning, right? Okay. All right, and that's it. When you have, typically most metamaterials actually will work in this limit, because most metamaterials actually have a roughly constant number of modes or constant number of self-stress, because typically that's when they are the most easier. That's when they are the easiest to control. Okay. Right. So now I had a quiz, but I don't have the time. I'm just going to ask the question, and you can think about it if you want. You can take a honeycomb lattice, and the inverted honeycomb lattice that we had, and you can ask how many degrees of freedom it has as a function of its size. So imagine you have a honeycomb lattice with m column, n rows. You can ask yourself, how does the number of the number of floppy modes minus the number of self-stress scale with the system size n by n. And you can do that by counting by just brute counting, and you can determine which solution is right by doing that. And the solution is there, right? But I don't have time to give it. So let me. Well, no, actually, I should give it because I need it. Here, what you find if you do that is that you find that actually the correct answer is 2 times n times m. And intuitively, you can understand it as the fact that each unit cell has 2 degrees of freedom. So if you have n times m unit cells, then you have n times degree of freedom. So you grow. And so typically, this metamaterial has a number of floppy modes that grows with the system size. All right. Here, another example that I like very much. These are squares that are rotated by the vertices. And you can do the counting. And here, what you find is that this object always has more states of self-stress than floppy modes. And actually, what you find in that case is zero. So you always have n0 minus ns is always minus 3. So you always have at least 3 states of self-stress. But here, interestingly, and that's actually to illustrate my point, if you have an ordered system, you allow for an extra test of self-stress, so you allow for an extra degree of freedom, floppy mode, and that's the one we use tomorrow in the next lecture. Whereas here, if you introduce some perturbation, some defect, what you will do is you will not allow for this extra floppy mode and not allow for these states of self-stress. So on the left, you have N0 is 1 and NS is 4. But on the right, you have N0 is 0 and NS is 3. Right? OK? And so this is to illustrate that typically metamaterials work around the limit of the coordination number, that is critical coordination number, that is discussed typically for disordered elastic lattices. But since you can have a lot of symmetries, that scaling here, where necessarily your number of floppy modes and your number of self-stress are constant, doesn't change with system size, is incorrect. Because you have a lot of symmetries, so you can really vastly deviate from this. Okay? And so to conclude, I actually have a little classification that I find useful for metamaterials typically, by just counting how many degrees of freedom they have, or how the number of degrees of freedom changes with the system size. Okay? So the honeycomb lattice that we discussed actually has a number of floppy modes that grows with the system size. That makes a very floppy lattice. On the other hand, this lattice that has a defect here is frustrated, so it has 0 degrees of freedom. What we mostly do in metamaterials is look at these single modes metamaterials, so only one way of deforming. This is, for instance, what the smiley cube was about. And recently, we found that, in fact, it's not the end of the story, because you can have some architecture, if you really look for them, that have more than one mode, but not a mode, but a number of modes that doesn't change with the system size. Okay, and so this is a potentially useful classification. If you want to make a metamaterial that has, one smiley face, then you need this. If you want a metamaterial that can do anything you want, then you need this, but then you need, many hands to manipulate it. If you want a metamaterial that has a few responses, doesn't necessarily need a lot of hands to control it, then that's what you need. Okay? Okay. And so, yeah.
I would add something between the honeycomb and the polygon.
Yeah?
The holographic one, where you have 0 in the bound and bound which sets your state, which is quite complicated.
Yeah, I guess you can also, I guess you can refine indeed the classification or have several shades of plurimode, I guess, right?
Or in the horizontal, because it's not plurimode. Because it's effectively on the bound is 0,
Yeah.
but the bound is holographic. That's
Yeah, but in practice, that still means that you need a lot of, you have like a growing number of modes, right? So I guess that's, yeah, but I agree you have different ways of growing with system size. You can grow with the surface, you can grow with the volume, or you can even grow logarithmically. You have, so you have like different ways of doing it. Yeah. And so to conclude, we only have 10 minutes left. I had planned an exercise where the idea was to actually not play it by intuition, but actually hard code the matrix that allows you to know how many floppy modes you have and how many states of self-stress you have. And I wanted to have you do it on these two examples here. And the idea is to do what we did, use Maxwell-Caroline counting, but not only that, to code up this compatibility matrix that you saw with Tom. I have published the partial solution on GitLab, where I actually code some of building blocks that you need for that. But I haven't uploaded yet the solutions. And I will do that later in the week. So maybe what I can do, we can stop now, take questions. And for those of you who really like to learn how to do that, I think it's a very useful exercise anyways. You can try to go through those steps. And if you need a head start, you can go on this GitLab to see how to get started. Yeah, and with that, I think I'm done, so thank you.
Okay, Corentin, just a point. So the idea there, just be clear about the notation that you have now. then these materials that you're proposing us to compute all that,
Mm-hmm.
is the white some holes, or is this more like
I'm going to show what I'm going to show my I'm going to show my code. Okay. So the way here I removed the no, this is the solution. So this is an example of a lattice, right? Where actually this is the lattice. So each node here are depicted by a red node, each bond by a black bond, and actually the arrows on top are the floppy modes, right? And so the way to code this is you have to define a matrix that encodes all the positions of these red nodes, right? And all the relationship between the bonds. So you have a matrix which is called the adjacency matrix that relates, bond number, node number 0 to node number 1.
right?
So you have but these are already coded. What I only ask is to code the how you construct the compatibility matrix from that. Yeah. And so I upload the solution, but I think in general, if you're interested in disordered lattice and metamaterials, that's a very good, painful but good exercise to do. So.
That's
Yes.
nice. So is there a question? More questions?
Just a technical question. So in the continuum picture, you show that colorful thing, right? There are these thin lines, and when you code the compatibility matrix, you assume that it cannot buckle, right?
No.
Just treat it as a bond.
Yeah, a linear elastic bond.
Okay.
Yeah, everything here is linear.
Okay.
Yeah.
I have a question. You said that there is no clear answer or rules to define a metamaterial from the basis, right? But I would say even having soft modes is one of the clear roles that you have to have. Is it right? So you have some clues, because I understood at the beginning that you said
but
there is no general things for that.
That's how we reason. We take objects that have a number of, for instance, a constant number of soft modes, but generically, I don't know how. You tell me I want a network that has this many modes as a function of system size. I don't know how to do it without starting from something I already know.
I see.
Right? I don't know how to do it from scratch without prior knowledge or prior, let's say, initial guess. So somehow you always have to start from an initial guess, which is nice when you know a bit, or but it's also a bit frustrating to.
Yeah, so you need to build your intuition somehow in order to.
Yeah, or library, I guess. So most people in the metamaterial field here are building libraries where they can shop from, right? That's what we end up doing, and then we just try to find ways to expand the library. And carefully search the library, let's say. Yeah, or efficiently search the library. Yeah.
Right. Other questions?
Could you go back to the example 5?
Mm-hmm. This one?
Yes. So for the disordered one, the right side one, you mentioned there are 3 self-stress modes. And how could I count it from the structure if I don't know the compatibility matrix?
You don't. You just know by. Okay. Well, you know and not minus ns.
Yes.
And you know because you've played with these that this doesn't have any floppy modes.
But how could I know there's no floppy mode before I count it?
Here I just know it because I've played with these structures for many years. Otherwise, there's no other way otherwise than calculate the compatibility matrix, look at its kernel, or actually print it and show that it doesn't fold, right?
So yeah, I'm also a little confused on how the counting for this one goes. The coordination number average is 5, right? So you have a lot of state of self-stress.
Yeah, this is yeah.
But you said 3?
I said 3 here. Yes, the counting is actually here. I think it's correct. So here I had the 40 nodes, and 80 bonds. And so when I subtract, I get 0 as a result.
Oh, so just for this particular system size. I see. If you make the system larger.
If you go to larger, it's
Okay.
going to grow. Actually, and typically, I think there's kind of a heuristic way to identify steps of substrate is to look at loops, but I don't have a very systematic way of doing it, I guess. Actually, this is an interesting game to try to spot them. That's where I think looking at the compatibility matrix is the best guess beyond that. Yeah. Hmm?
You're not an origami. If this is origami, there is a boundary calculated.
Maybe, yeah. Maybe, yeah. Yeah.
Then what happens if you have heterogeneity in terms of the stiffness of this, for example, the springs, or we can see that symmetry plays a big role here because of the counting between the modes and the stresses. So if you don't have general rules to build a metamaterial, then those things are not, I mean, as soon as you put some heterogeneity or some asymmetry, then things becomes much more complicated to predict what's gonna happen. Is it true?
Depends which kind of heterogeneity. You have different types of
disorder. So for example, if you put asymmetry in this or heterogeneity in terms of stiffnesses between the
stiffness don't do anything here. I'm just talking about bones topology, so it doesn't matter. But of course, putting a bit of positional disorder does. Right?
Yeah.
So I think different disorders do different things. But here you can see at this level of this argument, it's only topology. So if you have a state of self-stress with slightly different stiffnesses, that doesn't matter at the end.
So that's just for linear. I mean,
Sure. Everything here. Yeah.
If you had a hierarchy of stiffnesses, then for the nonlinear response, it'll completely determine everything.
Hmm.
Right?
Yeah.
So you just go in order of which bonds are stiffer. Yeah. That.
and then you can predict.
Well, you have a hierarchy, so you have to solve, for each scale. But it's not so good for the nonlinear.
But for the nonlinear, you will have to redo that every time. You have to deform a bit, then redo your analysis, deform a bit, redo your analysis, right? Yeah, I guess.
Okay, so let's thanks again Corentin. And we do have a break.
I can upload the slide.